Okay, welcome to today's lecture. Today's lecture is about collisions theory, Arrhenius equation, and activation energy. So before I can start, just ensure that you subscribe to this channel so that whenever I'm going to be posting, you will be notified or updated. So let's start with the collision theory. So what's the collision theory? The collision theory of chemical kinetics gives the idea that the reacting molecules must collide with each other in order for chemical reaction to occur. So for any chemical reaction to occur, there must be reacting molecules that must collide with each other, or these same reacting molecules, they must be in physical contact with each other so that they produce a chemical reaction. If you are not having any collision between the reacting molecules, or if there is no physical contact between the reacting molecules, then don't expect any chemical reaction. And then note that the collision theory states that the rate of a reaction is proportional to the number of collisions occurring per second between the reacting molecules. So this is what I'm from saying there. So here you're having rate which is proportional to the number of collisions occurring per second, like that. Now we need to know about the collision model. So what are you supposed to know here? Note that in a chemical reaction, bonds are broken and new bonds are formed. Molecules can only react if they collide with each other. So for a reaction to occur, there must be molecules that must collide with each other. There must be in physical contact. So this thing will help us understand whatever I'm from explaining there. So for the reactants to collide successfully, you need they must collide with enough energy. So there must be that enough energy that to initiate a chemical reaction. So this molecule, this one molecule you're seeing, this green molecule, will collide with this molecules here, and it will collide with these molecules with enough energy. So when this comes in this contact with this, it will look like this. And as you can see, this green molecule is attaching to the green molecule because the reactants must provide the correct orientation between the reacting molecules. So there is that proper orientation between the reacting molecules. So the green one is attached to the green one, and then this collision here, since this green molecule is attached to this with these three molecules with high energy, so there will be that bond breakage. When after that bond breakage, you're going to have these products here. So it will produce this after the collision. So this is what you're supposed to know here. And then we need to know about the activation energy, which is very much important. So what is the activation energy? So activation energy is the minimum energy required to initiate a chemical reaction. So for any chemical reaction to occur, there must be that minimum energy that will initiate a chemical reaction. If there is no that minimum energy, if there is no activation energy, then you can't have a chemical reaction. Note that activation energy will vary with the reaction. And then this picture will help us understand what activation energy is. So for example, you're having a ball. So a ball cannot roll over this eel if it does not roll the eel with enough energy. So there must be enough energy for a ball to roll over this eel. So same applies with a reaction. A reaction cannot occur unless the molecules possesses sufficient energy to get over the activation energy barrier. So I'm sure you understand this now. And then here let's look at the endothermic and exothermic reaction. So you're having A plus B reacting to produce CD there. Okay, now let's look at exothermic reaction. So here, as you can see, you're having potential energy, which is plotted against the reaction progress. You're having your two reactants here, which is A plus B. So this there must be enough energy to reach the activated complex. So when this reaches the activated complex, just know that you're going to have your products. So this product you're seeing C and D, it's because of there was enough energy between the reacting molecules to reach the activated complex. And then we can call this A plus B this side as the forward reaction, while this CD going backwards, like that's a reverse reaction. So it's very possible for a reaction to go in the reverse way like that. And then this is your activation energy. as you have seen here. Now let's look at the exothermic reaction. Same, as you can see, the potential energy projected against the reaction progress, but this one is starting down here for the endothermic reaction. Sorry. So as you can see here, this A plus B, there is that collision. There is that enough energy between these two reactants. So that enough energy, it's making it to be going up like that, and when it reaches the activated complex, just know that you're going to have your products like that. And then as I said, going this side, that's a reverse reaction, and then from this reactant part going this side, that's a forward reaction. And then your activation energy is this one you're seeing here. So as I said, the activation energy is the minimum amount of energy required to initiate the chemical reaction. Okay, and I'm sure you're clear here. Okay, now let's look at this part now. So taking these factors into account, we can take the rate constant as this. So rate constant is equal to AE to the power negative AE, which is the activation energy over the gas constant and the temperature there, as you can see like that. So I'll explain more about this. And then so this equation you're seeing here is the Arrhenius equation, where A is called the frequency factor. And then here what you need to know is AE on top, the power, that's the activation energy over the gas constant, and then that's the temperature you're seeing there, and then this K is the rate constant. Now taking the natural logarithm both sides of the Arrhenius equation, we get, so if you introduce the natural logarithm both sides of this Arrhenius equation, this side and that side, doing mathematics there, calculus, so you're going to have the equation to be like this. So you're going to have in K, which is equal to negative E on top, having the activation energy over the gas constant, and open bracket 1 over the T, the temperature, close bracket, plus in A like that. And then where K is the rate constant, EA, that's the activation energy, which should be in kilojoule per mole. And then R, that's a gas constant. T is the temperature, which should be in Kelvin. And then A, the one you're seeing there, that's a frequency factor. This capital letter A, that's a frequency factor. And then small letter a, that's a constant, indicating how many collisions have the correct orientation to reach the products. So that's what you're supposed to know here. So you can use this equation to find the activation energy. So I'm going to show you how this is done, so just pay extra attention. So apart from this equation, there's another equation that can be derived from this equation, so pay extra attention so that you can understand. So as I was saying, however, activation energy also can be calculated from the values of K at only 2 temperatures. So you're having 2 temperatures by using a formula that can be derived as follows from the equation. So you are using 2 temperatures. We are having temperature T1, where the rate constant is. So the same equation, this equation which came from the Arrhenius equation after introducing the natural logarithm. I'm sure you know where this thing is coming from. So here, it's T temperature. It's at temperature 1. So you are seeing K1 there, T1 like that. And then now, what about temperature 2? So at temperature 2, where the rate constant is this. So as you can see, this first equation and this second equation, that's the same. What's different here is that different temperature. So the first one here is at temperature 1, this one is at temperature 2. So yeah, as you can see, there's there's K2 there, T2 there, just like that. And then subtracting first equation from the second gives, so when you subtract this first equation from the second equation, what are you going to get? You're going to have something like this. So this in K2 minus in K1, it will look like this. And then this whole thing you are seeing here minus this whole thing you are seeing there, it's going to look like that. And then here, after subtracting, you're going to notice that this in A and in A will go, because in A minus in A will go, that's 0. And then here you're having this negative and this negative, so it will become a positive. So this is a positive you're seeing here, so it will look like this. And then here, what do? You will take this one with one that side, and with this negative will come this side. So when you take this this first equation, which is at T1, this side, it will look like this. So you're going to have an equation that will look like this. So what have you seen? What's happening to the first part here? here they use the laws of indices. When you are subtracting, which means you are dividing. So in K2 minus in K1, it's going to be over. That's laws of indices like that. So it will be in K2 over K1 like is equal to, and then you can wonder why this negative is not appeared in here, because you had to take this face which is having T1 here, this side, and then this is the one which is having T2 there, we had to take it this side, and then after that we had to factorize on top with the activation energy. We factorize, you're going to have 1 like that. So this is the 1 ones you are seeing there, and then down there we had to factorize the R constant, the gas constant there, which is going to, we're going to remain with the temperatures like that. So the negative had to disappear because we had to take this part, this side, and then the other part, that side, and after that we had to factorize the activation energy, we had to take it out, and the gas constant, we had to take it out like that. So the final equation will look like this, and then this one we can also use it to find the activation energy, and I'm going to show you how that is done. Hope it's clear and you can understand whatever I've done here. Okay, now let's do an example so that you can understand clearly. So what's the question saying? So the question is saying the gas phase reaction between methane and the atomic sulfur is given by the equation. So we are seeing this methane reacting with the atomic sulfur to produce this and that. So at temperature 550 degrees Celsius, the rate constant for this reaction is 1.1 L per mole. So that's liter per mole. Now per second. So here you have been given the temperature and the gas the rate constant, which is this, and then at 625 degrees Celsius, the rate constant is given to be 6.4 liter per mole per second like that. So you have been given at this temperature 625 with its rate constant. So you have been given two temperatures, and these same two temperatures, they are having their rate constants. And then using these values, calculate the activation energy. So they want the activation energy for this reaction. So you can come up with solutions, and then here you need to come up with your data. Your temperature should be in kelvins, but it's in Celsius. As you can see, these temperatures are in Celsius, so you need to convert these temperatures in kelvins. You need to add them with the 273. I know by this time you know how to convert. And then you're having these rate constants. So what are you supposed to know? You're supposed to come up with a table which will look like this. So that's your data now. So you need to collect this data. So as you can see, these are your rate constant. So at temperature 550, we're having this rate constant, which is 1.1. And then with this temperature, it must be in kelvins. So when you add 273 to this 550, you're going to get this, which is 820 at T1. And then we are having at the temperature 625, we are having our rate constant to be 6.4. And then our temperature is not supposed to be in degrees Celsius, but in Kelvin. So you need to add the 625 plus 273. You're going to get 898 like that. And then here you can come up with your formula so that you solve. So here they want the activation energy. So note that here they are looking for the activation energy, which you don't know. So which formula we're going to use? So the one I'm from showing you, you're going to have in K2 over K1 like that is equal to the activation energy over the gas constant like that. Then you're going to have 1 over T1 minus 1 over T2 like that. And then here, what are you supposed to do? You can make activation energy with substitute formula. So you can multiply this activation energy times this thing that is in the bracket. So when you multiply, you're going to have activation energy times, when you multiply with everything in the brackets there, it's going to be 1 over T1 minus 1 over T2 like that is equal to, and then this you can say over 1 close multiply other times in K2 K2 over K1. So you're going to have R in, then you can say K2 over K1 like that. And then here, what do? You want to remain with the, and then here you want to remain with the activation energy. So what do? You say over 1 over T1 minus 1 over T2 like that, over 1 over T1 like that, minus 1 over T2 like that. Then what do? You cancel here, so your activation energy is equal to the gas constant in K2, sorry, so it will be K2 over K1 like that, over 1 over T1 like that, minus 1 over T2 like that. And I'm sure you have seen what's happening here. So here my thing is not allowing you to write T1 there. I'm sure you have seen what's happening there. And then here, what do? You can substitute. So what's your R? Your R, this one, is 8.3145, which would be joule per kilojoule like that, per mole like that. And then your R, so you need to substitute. So R is 8.3145 joule per K like that, more times what's your K? So your K, your K2, which is according to the table, your K2, which is this one, which is 6.4 like that, over what's your K1, which is 1.1 like that, over what's your, you're going to have 1 minus what's your T1. So your T1, your temperature one there, that's 8.3 minus 1 over what's your temperature T2 there, that's 898 like that. And then when you work out everything here, you are going to, so you need to multiply this gas constant 8.3145 times in. So here, don't forget in, I forgot the in of 6.4 over 1.1. So on your calculator, when you work out that, and when you work out 1 over 823 minus 1 over 898 on your calculator, when you do this on your calculator, you're going to get your answer to be, your activation need to be 1.4 times 10 to the power 5 joule per mole. So that's your activation energy. So your activation energy final is equal to 1.4 times 10 to the power 5 joule per mole like that. So that's how you come up with, that's how you solve this type of equation. And I'm sure you are clear and it's not hard. And then this is your question. These are your questions, your task, and these questions are part of your theory sheets. So I want you to solve question 8, and you can also try to solve question 9, and you can submit the answers. And then for tuitions, it's 100 kwacha the course, so you can deposit, and if you're interested, that's if you are interested, you can deposit in these accounts numbers you're seeing here. And then last, you don't forget to subscribe, like, share, and comment. And thank you for watching.